we have like everybody is like from the physics department except maybe you two.
Right.
And so who are you?
So this is my son
People who are
Salsa.
interested in science.
Yeah. He's a middle schooler in Jeffco over in Lakewood.
Over in Lakewood, okay.
At Peyton Middle School.
Uh-huh.
And I was just trying to remember where I heard about this. I have no idea, but I put it on our calendar and we showed up.
Well, so what I want to say is that these guys don't get to ask questions, but you get to ask as many as you want.
Well, we may be here a long time. You might regret that.
Okay, so it's funny, you get to the end of your career and you ask yourself, what was my career about? And I discovered one day that my career was about nanoscience, that everything that I've worked on has in some way involved things that were nanoscale in size. And what I want to do is I think there's maybe one equation, without many equations, to run you through some ways to think about nanoscience. And what we're going to be spending a lot of time thinking about is waves, because in order to take advantage of nanoscience the way I like to, which is in things that are optical or things that conduct electricity, I worry about the wave-like properties of matter, and those are things that you can manipulate through nanostructures. So all the physicists that are here know about wave-particle duality. I just kind of want to point out a few things. Basically that it's been a big debate. The idea that light was made up of particles was like as early as the 11th century that was believed. And it makes sense when you think about it. You put a hole in something, you shine light through it, you get a shadow behind it. It's like particles came in, and they were blocked in some spots and weren't blocked in other spots. And around the 17th century, people started proposing this other kind of view of light, that maybe it was made up of waves. And then you had Newton, and Newton's like our favorite guy, right? I mean, Newton's the man. But Newton had it wrong. He said it was particles. Light was made up, the corpuscular theory of light. I just like saying that. Could everybody say that with me? Corpuscular. Yeah, good. Okay. And then around the 1800s was when everything got really interesting, because people started doing diffraction experiments. And from diffraction experiments, they could tell that light was made up of waves. And then people started doing things with matter, like Avogadro's number and Mendeleev and the periodic table. And so things became clear. Matter was made of particles, and light was made of waves. And that was a good world. It was a great world to live in. It was a simple world. When you looked at things, everything made sense. And then it all got messed up, because Albert Einstein came along and realized that when light interacts with matter, it behaves like it's made up of particles. Whereas when it's propagating, it behaves like it's a wave. And then other people came along and discovered that when electrons and protons and things like that move, they seem to show some wave-like properties. And so what we ended up with is a situation where neither a particle picture nor a wave picture can describe light or matter. You need both pictures in order to describe it. It's something that doesn't fit into either. And this is known as wave-particle duality. Let's see, got too far. So light and matter both exhibit wave-like and particle-like properties. Typically, when you're exchanging energy, when you're absorbing energy, you start to see the particle-like properties. But when you're looking at transport, when things are moving, lots of times that's where you're seeing sort of the wave-like behavior of the material. I put in a cartoon for you guys. What do you think? Okay. Let's see. So, what I want to talk about is using the wave-like properties of light and of matter to do interesting things, to do nanoscience, to do things that we can't normally do. And so we have to know a little bit about waves. What do they do? And in particular, what do they do that particles don't do? So the first question, reflection. Is that something waves do that particles don't do? Come on, show of hands. How many think it is? How many think it isn't? Oh, good. Because usually nobody raises their hand both ways, and that means everybody's kind of stuck in Yeah, so waves will reflect off of a mirror, and particles will bounce off of a mirror. And angle of incidence equals angle of reflection, and everything's good. So what about refraction? That's where light bends going through a glass or a prism. This is a little harder. What do people think? Is this something that just waves do, or can you come up with a particle theory that does this? How many think you can? How many think you can't?
Depends on how many flaws you want in it.
Well, it turns out that Newton actually solved this, and he could come up with a model where particles would refract. Hello? What are you looking for? Nothing. He could come up with a model where he changed the speed of the object, of the particles when they went into a new medium, that actually gave refraction. Okay, what about, keep doing this too many times. Can't get it. There we go. What about diffraction? Diffraction is, so, you know, if you have a radio here and you're over here, you can actually hear the radio. You don't have to be in line of sight to hear it, okay? Things bend. Is that a particle thing, or is that just a wave thing? How many think it's both? How many think particles? How many think waves? Yeah, this is pretty much a wave thing. The idea that waves bend going around corners is diffraction, is something that comes about from wave-type behavior. Okay? Gotta be careful here. Superposition and interference. This is also a wave-like thing. Superposition is where two waves can actually go through one another when they're on top of one another. If one wave is pointing up and the other wave is pointing up, you get a wave that's pointing up even further. If one's pointing up and the other one's pointing down, they can cancel out. And this is kind of a neat video. This guy here has two little balls, and he's bouncing them in the water and creating waves. And you can see these circular waves going out from each ball, but when he gets them both going, the waves from each ball are going to interfere. And you can see that. And you start to see the interference pattern build up. And when he gets finished, so we have these lines, these nodes that are going through there, and that's where the crest of one is falling on the trough of the other, and these guys all know this because they see this all the time. But superposition and interference is a wave thing, and we can use this very effectively to engineer materials when we're working with nanostructures. Okay, so why don't we notice the wave-like particles properties of matter when we can easily tell that sound is a wave? I mean, you know, you put a radio over there, it bends around the corner, you hear it, have a train coming at you, it whistles, the whistle's high-pitched and it's low-pitched when it goes by. So it really has to do with size. In order to observe the wave-like properties of matter, the obstructions, the objects that you put in the way, have to be small compared to the wavelength. If they're large compared to the wavelength, you can get basically what looks like just a shadow. And that's why Newton believed that particles, that light was made up of particles, because he couldn't make things small enough to see the wave-like behavior of the particles. They just looked like the wave-like behavior of light. They just looked like particles going through a hole. So size is the key here. It's not going to do it, huh? Ah, there we go. So, some size scales. A wave on the ocean, you measure it in feet or meters. By the way, I wanted to ask you guys, have you ever seen a wave come into shore like perpendicular to the shore? Why is that? Come on, physics dudes. I mean, in the ocean, they must be pointed in many different directions, right?
You guys more of a shock wave, I guess, than...
Yeah, well, that's an interesting answer. Probably not right, but it's interesting. No, that's good. Okay, so tell me about the speed of waves on water. So the shallower the water, the slower the speed. So as the waves come in towards shore, if they're angled like this, the side that gets to shore first slows down, and the wave bends toward the shore. So at the shoreline, the waves are always coming in toward the shore. Now, you've heard about waves breaking and seen people surf, right? That's exactly why waves break, because they have to conserve their energy. They come into the shore, they move slower, they have to get taller so that they have the same amount of energy per unit whatever, and that leads to the waves breaking. So that's kind of a cool thing, I think. Anyway, that's how we can change the index of refraction of waves in a water tank. We just change the depth of the water. Okay, so sound. Sound is, you know, at a kilohertz, it's about 1/3 of a meter. Now, a green light in a laser pointer, like the one I have over there, that's 532 nanometers. 532 times 10 to the minus 9 meters. So that's much smaller. It's very easy to make things that are the scale of sound waves or ocean waves, but it can be very hard to make things that are the scale of green light. And electron accelerated in a cathode, you guys know what a cathode ray tube is? That's what TVs used to be before they were LCDs, right?
When it was black and white.
Yeah, when it was black and white. Because when I was little, TVs were black and white, and my best friends were dinosaurs, and we watched television together. Okay, so an electron accelerated in a cathode ray tube will be about 0.04 nanometers. That's its wavelength. So it's hard to see wave properties of these materials unless you can build things that are down at that scale. So this is sort of one of these size lines that you see, and just for the kid that's in the audience, this is a logarithmic scale. Each number is a factor of 10 smaller than the one before it. And what you can see is that ocean waves and sound waves are over here. They're you know, beyond the end of this scale in terms of their size, whereas light waves are about right here. Electron waves are in this region. And that's the region where nanoparticles exist. So if we want to scatter those waves, we want to do something with them, nanostructures are the right thing to use. A semi on a highway. Its wavelength is clear down there.
Why?
So that's why you never see a semi on a highway go through a toll gate and all of a sudden veer off to the left and diffract. Because its wavelength is just too small to do that. Okay? You guys learned something, huh?
What's a human on a highway's wavelength?
Huh?
What's a human on a highway's wavelength?
Okay, so let's see. I'm really not doing well with this. So now some examples. And this is a first example. It's a really simple example. I just want to show it to you. What we're going to do is we're going to build up a film, a material. And we're going to build it out of materials that have two different indices of refraction. They bend light differently. And you guys know about index of refraction. You think you don't know about index of refraction, but you do. Because, well, none of you wear glasses. You wear glasses. You do?
Yeah, I'm just not wearing them.
Well, you go to the eye doctor and you get an exam. And at the end of the exam, the doctor says, let's figure out your glasses. And then they give you choices for lenses, right? And they could be plastic lenses or they could be glass lenses. And there can be high density plastics. And depending upon, particularly for someone like me, depending upon which glass they give you, the glass in your lenses will be thicker. And that's because the glasses have different indices of refraction. And you need a thicker lens if you have a lower index of refraction to bend the light the same amount. So what we're going to do here is we're going to build up a layered structure out of transparent materials, things that light go through. They're glass with different indices of refraction, or they're materials with different indices of refraction. But when we build these layers up, we're going to make them a perfect thickness so that when the light comes in and bounces off of this one, it interferes with the light coming in and bouncing off of that one. Actually, this picture's wrong because there's going to be a bounce here and a bounce here. And the reason you're going to get bounces is because those are different indices of refraction. Now, if you make the thicknesses right, you can build something called a distributed Bragg reflector or a Bragg mirror. And this is a plot. You know, think I have a laser pointer. If I have two things in my hand, though, it could be really dangerous. Let's see. So, this is just a calculation of what the reflectivity of a stack like this would be if you made it with 5 layers, if you made it with 9 layers, if you made it with 13 layers, if you made it with 17 layers. And can you guys see that the reflectivity right here is getting higher as you add more layers? So here you have something that is made up of materials that individually are transparent to light. You look at them, you can see through them. And yet you can build something which is not transparent to light, which reflects light in this wavelength region. And this is actually the reflectivity as a function of layers, and you get up to 15 or 16 layers, and you can produce a mirror which is nearly 100% reflecting. That's kind of cool, isn't it? Now, this is a simple example, and you guys have seen examples like this. An oil film on water is like this, right? It has a reflection from the top surface, a reflection from the bottom surface, and it does something very similar to this. But the cool thing here is that you can use this to make a mirror, and this is actually a one-dimensional photonic crystal. It's the simplest photonic crystal that you can build, because you're making the spacing between these things be like atoms in a solid, so that the waves bounce off them in a way that they constructively or destructively interfere. Now, you got to remember this one because I'm going to use it later. This is a Bragg mirror, and we can build a mirror that is very highly reflective out of multiple layers of things that just have a difference in index refraction. Remember that one. Okay? Now we're going to talk about stained glass. This is another example. Now, you guys have all seen this. Nancy is up there. And Nancy and I went to France last year for her birthday. It was, which birthday was it last year for Nancy? Guys.
25, 30.
There is only one answer, 29. And next year's birthday will be what, guys?
29.
Very good. You've learned something. This will come in handy for you in the future. Okay. So, you know, you see this stained glass. This was at the Musée de Cluny, and this is a stained glass window that was taken out of a nearby church, Saint-Chapelle. And you can see that particularly the reds in here are really vibrant. And this is like 500-600 years old. And you know, you take like the paint on my house and set it out in the UV for 500 or 600 years, and what do you think it's going to look like? And this stuff didn't fade. This stuff doesn't fade. And so the question is, what's going on here? How did they get these colors in the stained glass? And the way they did it was by introducing metals into the glass. So for instance, they added gold chloride to the glass, and if they added it just right, they would get this vibrant red color. And they added silver nitrate to the glass, and they could get colors from orange through yellow. It really is hard. You have to use the right temperature. You have to use the right length of time to cool it. So you guys know what's happening here, right? They were actually producing nanoparticles in the glass, gold and silver nanoparticles. And the interesting thing is that gold and silver nanoparticles, now gold is inert, silver is pretty inert, so these are things that won't oxidize, they'll last a really long time, several hundred centuries. And it took a while to figure this out. But what's going on is something called the surface plasmon resonance. Now here's the right way to think about this. Here's my nanoparticle, and it's made up of atoms. What are the charge on atoms? You get to answer. What was your name, by the way?
Celso.
Huh?
Celso, I'm...
Celso. Okay.
So what was the charge on atoms?
What, the nucleus of an atom, what's positive or negative?
Positive, because there aren't any electrons.
That's right. So what we have here is we have a bunch of positive atoms with a bunch of negative electrons around them. And we bring in an electric field, a wave, light, and it pushes the electrons to one side, and now the negative and positive charges are separated from one another, right? And so they're going to want to get back together, right? There's a restoring force. And you guys, especially the physicists, are very familiar with something that you pull it apart and it wants to come back together. And it is the model for all of physics. And what is that thing? A mass in a spring. This is a simple resonance. It's a mass spring system. And it turns out that it'll have a particular frequency where it resonates. And at that frequency, it will absorb and scatter light really effectively so that the light doesn't go through the glass. And the only light that goes through the glass will be the light that is non-resonant. And in the case of gold nanoparticles, that resonance is in a place where it gets rid of the blue light and lets the red light come through. Now, you guys are familiar with resonances like this. Another example is sound waves. We can hit a glass with sound waves, and we can tune the sound waves to the frequency where the glass goes back and forth. And if we do, what happens? The glass moves until it eventually breaks. People back at our school actually hit things like this with lasers that are so intense that it rips the electrons off of them, pulls the atoms off of them, and breaks them. Just like this, because you can excite this kind of a resonance. So a plasmon resonance, this is a way of interacting a wave with matter in the nanoscale and producing colors. This is a paper where they use silver nanoparticles, and these are all the different colors they could get by changing the shape and size of the silver nanoparticles. Now, I need to know, is this useful? Or is this just, physicists playing around in the lab? And try damn chemists. What could you use this for? Yeah?
Probably art.
Yeah, definitely for art. I mean, it's great for art, and has been for quite a while. Turns out there's a mission to Mars where they're using these as optical filters because they're worried about them, the mission has to last a really long time, and they're worried about the filters degrading under UV illumination and things like that. This was actually taken from a paper in textile science, and they are using the nanoparticles to dye wool and to dye cotton and things like that. And part of the reason they want to do it is because silver nanoparticles in particular kill bacteria. These resonances that you can excite on the surface actually produce large fields that will destroy bacteria, and then the silver itself is a little catalytic, and so it'll destroy bacteria. So people are looking at this as a way of making fabrics that are colored and are antimicrobial. So science can be useful. Okay. Just a reminder, remember the two balls bouncing in the water? This is just a picture of that. We send light waves in here. We go through a small slit that causes diffraction. Then we go through two slits. Then we get interference, bright and dark patterns, right? That's with light. Now we want to start talking about matter waves. What if we could do the same thing with matter? What if we could send electrons down toward two holes in a screen, and we could put a magnetic field on it? The magnetic field is like an index of refraction. Things that go one way around the magnetic field slow down. Things that go the other way around the magnetic field speed up. And if we change the magnetic field, we can create two maxima here and get a big matter wave interference. Or we can have a maximum and a minimum here, and we can get zero and get no interference, right? Get no matter wave right there. And so this is an effect called the Aronoff-Bohm effect. And it's the double slit experiment, but it's done with matter waves rather than with light waves. So here's how we do it. We make a wire. And the wire comes down like this, and then we split it in two. And of course, if matter is made up of particles, then the particles are going to go one way around or the other way around, but they aren't going to go both ways around, are they? But if matter is made up of waves, the wave can propagate along both sides, and we can get interference over here, and we can see that interference. So the next slide is going to show you that it works, right? Okay. Did you see the animation there? Let's go back and do that. That took me a bit, Watch it.
Wow.
Now, the most important thing for you to know about this paper is that it was written by 4 people that I worked with when I first went to IBM back in 1985. That's why I put their work on here, because I thought it was so cool at the time. I was there on a Saturday when they came running in and said it worked. So what they did was they made metal loops.
Oh, that's not on my knee.
What?
They made metal loops out of gold. The loops are actually pretty large, but the width is kind of small, 40 nanometers. They looked at the current going through here as a function of the magnetic field that they ran through it. And sure enough, as they changed the magnetic field, the current going through the loop, the resistance of the loop, has oscillations in it. And for those of you that care, those oscillations are H over E in field. They have to be. So that's pretty cool. Now you can see that it's a little noisy, and it turns out this is a very small fraction of the actual current that's going through the thing. It's hard to get this effect. But more recently, people have been doing this with, if you want things that can travel a long ways and don't scatter, don't decohere, you want to use not gold, but you want to use something that has a really long, mean, free path. And that would be what? What's our favorite material today? What do we make pencil lead out of?
Graphene.
Graphene. So this is a Aronoff bone ring built out of graphene, and you can see the dimensions here. And you can see these are really nice oscillations. And in fact, there's a beat frequency on top of it, and people argue about what the beat frequency comes from. So this is pretty cool. What could you use it for? Anybody got an idea? Well, how about a magnetic field sensor? Yeah. People are talking about that. Turns out that in electron microscopy, some of the students here may have used a phase contrast optical microscope. It's something that looks at the waves bouncing off the surface and interferes them, and you can see features that way in an optical microscope that are smaller than the wavelength of light, so you can kind of beat the diffraction limit. This is the highest resolution that you can get, is to actually look at a magnetic specimen in an electron microscope and use the phase difference for light traveling, or electron beams traveling through different parts of the sample to interfere with one another. And you can get the highest resolution that you can get in anything today is with that. Essentially, you're not going with that in an electron microscope. And someday we may be able to build electron waveguides on a chip, like we presently build optical elements on a chip. And instead of running electrons around as current, we'll run them around as waves and do wave computation on the chip. And that'll be pretty cool when we can do that. Nobody has any questions? Think this is going to work? It didn't. Okay, so I have to talk a little bit about optical absorption and optical emission. The way optical absorption works, optical absorption almost always involves electronic transitions in material. You have an electron which is in one state, you bring light in, the light gets absorbed and kicks the electron to an excited state. Now this sounds complicated, but you guys are kind of familiar with it. I brought along an example. Here's a UV light source. And here's a piece of paper. I shine the UV light source down here. You don't see anything. You can look at the UV light source. There's not too much there, right? And I hit the paper with it, and voila, we have a lot of light coming out. The reason that happens is because the paper has a dye in it to make it look white. And that dye, we're able to kick electrons up to an excited state with the UV light from the lamp, and then they drop back down and re-emit. And black lights, things like that, right? That's how this works. And so this is a common process in materials, where light comes in, causes an excitation, then it de-excites. Now, the question is, this is for a wavelength that can be absorbed. But remember, light is, we have wave-particle duality, and when it's traveling, it behaves like a wave. But when it's interacting, being absorbed or being emitted, it acts like particles, and those particles have a specific energy. So if the wavelength is a lot longer, what happens to the energy of those particles, which are known as photons? Long wavelengths are high energies or low energies? Low. So the photon energy goes down. So what happens if we have a photon that is red instead of blue? It's at a lower energy. It just goes through. So this is meant to show you that if you have a material and it has a ground state and excited states, for an energy larger than that, you can get absorption. For an energy smaller than that, you won't. And this somehow sets the color of the material, if you will. It's like, what wavelength does it emit? What wavelength does it absorb? What color is it interested in? So how can we tune the color of a material? This is a really good question, because we want to do that. Well, we could build a new material that's a different color. And guys like him who do all kinds of computation, they're all the time worrying about doing that. How do I make a material that has a different band gap? But that isn't what we're going to do. We're going to use our new knob to change the color of the material. And our new knob is what? What's it talk about? And so what's our knob? Size. Our knob is size. Okay, so we have to, well, I got two of them. Wave-particle duality. If this were light waves, this one's a long wavelength, and this one's a short wavelength. And so the long wavelength will be lower energy, and the short wavelength will be higher energy. And the same is true with matter waves. If you can make the wavelength shorter, then you can raise the energy. And how do we do that? Boy, this is terrible. How do we do that? We put the matter wave in a box, and we change the size of the box. And if we can change the size of the box, we can shorten the wavelength, and we can raise the energy. Those are our nanostructures. So here's the simplest box. It's a series of what are known as quantum wells. And I'm going to ask you guys a question, because this has been bugging me like for 2 days since I started thinking about this. It's one of these things you get in your head and you can't get free from it. So if I said that our technology just discovered something new and it's going to be a quantum leap forward in what we can do, would that be big or small?
Schrodinger's cat neither unless we check.
Yeah, you're right, actually. But in everyday parlance, is a quantum leap big or small?
Generally.
Big. I mean, you know, it's going to change the world. But a quantum is like the smallest thing. It's hard to see. So how did quantum get reappropriated by industry and turned into something big? I don't get it. Okay. Now, the way these wells are set up, I'm in a ground state, which means I only have one oscillation, one wavelength inside the well. And now I change the size of the well. These are materials we can actually grow. There are machines that are designed to grow things like this. One of the machines that is used to grow stuff like this is called a molecular beam epitaxy, otherwise known as an MBE. And when I was a graduate student, we said MBE stood for megabuck evaporator, because they're very expensive. And what they do here is use two crystals whose lattice constants are exactly the same, but where one creates an energy barrier to the other one. And so you can, on a wafer, grow a structure like this, where you have wells of different width. And as you narrow the well, you make the wave function shorter, and you raise the energy in the well. You raise the energy of the ground state. And now you understand what I was asking you.
Yeah, no, it makes a lot of sense.
So, why won't it wake up and do this? There we go. So now, we're going to send in light on a structure that's grown like this. And the light is going to excite carriers from one level to the lowest energy level up here. And here it's going to be a big excitation, and here it's going to be a smaller excitation. And then we're going to look at the emission from the sample as these carriers relax. And there we should get a big energy, and there we should get a small energy, denoted by blue and red. And in fact, this works just fine. This is a sample grown like that, and this is the emission spectrum, which actually Connor measured. And you can see you have multiple peaks in the emission spectrum. And each one of these peaks can be associated with one of those wells. The well that is the narrowest gives the shortest wavelength, which is the highest energy. So we can use size to tune the energy of the material, to change the color that it emits, which is pretty cool. That means we don't have to develop a new material. We can just quantum confine the material that we've got. And here's another example. That material that we just looked at were slabs. They're confined in one dimension. These are silicon quantum dots. They're confined in 3 dimensions. And in this experiment, what we do is we put these silicon quantum dots into an etching solution. And the etching solution slowly takes off the outer layer of atoms. And as you take off the outer layer of atoms, the quantum dot gets smaller. And as it gets smaller, its emission energy should go up. And what we're going to do is look at this graph here, which is just basically the emission from these materials as a function of time while it's sitting in etch. This is wavelength, and up there you're going to see the peak position plotted as a function of etch time. And what you see is try it again. No double bounce. I'm just going to go backwards because I think it's confused about where it's at. See how it's moving to the left as we etch. And we're moving from a material that was emitting in the infrared to a material that is emitting in the green. And you can see it in the vials there. So we can tune with size. Okay. Now I have to tell you how a laser works. Because what was the talk about? Butterflies and lasers. We all know how butterflies work, but now I have to tell you how a laser works.
Yeah.
And on campus we offer a course in laser science, right? And you guys have to go and sit in that class 3 hours a week for an entire semester. And I am going to give you how a laser works in 5 slides. Huh? Don't tell Chip. Okay, so these are our 2 levels that we had before. Come on. And I'm going to describe first spontaneous emission. Spontaneous emission is where the electron de-excites and it gives off light and we just don't know where the light's going to go. And so it looks something like this. You know, the light just goes where it wants to. Now, there's another thing called stimulated emission. And this is stimulated emission. A photon comes along and it causes the electron to de-excite just by the photon being there. And when the electron de-excites, the wave that it emits is exactly coherent with the wave that comes in. Now this sounds weird, but you guys are all familiar with this. You take 2 tuning forks. You hit one and you hold the other one near to it. And what happens to the second one? It starts moving a little bit. A sympathetic vibration, right? Or you take your violin and you bring it over by the piano and you hit a key on the piano and you start hearing the violin string oscillating, a sympathetic vibration. The math of this is a lot like a sympathetic vibration. Basically, by sending that one light wave along and having that electron see it, it causes the electron to want to de-excite and emit the same energy, and in phase. Okay, so stimulated emission, good, we've got that. Now, to make a laser, we only need one more thing, mirrors. So now we have our active medium, we have a mirror here, and a mirror here. Now that mirror is perfect. And this mirror is just a little bit crappy. It's like 99.9% mirror. So a little light can leak out, right? And so what happens? Photon comes along, gets stimulated emission. Then these two come along, more stimulated emission. The cavity builds up a lot of energy, but a little bit of it leaks out. There you have it. That's how a laser works. All you need to make a laser is a gain medium, this thing you can excite, and you can excite it optically or you can excite it electrically, and mirrors. And that's it. It's so simple. I could have gotten a Nobel Prize for that. Okay. So now, semiconductor lasers are real common. They're in everything. They're in this laser pointer that I have here. They're in your television remotes now. They're all over. And this is the way that they're conventionally made. We grow the laser up this way. This is the quantum well layer that you can use to tune the energy of the laser by changing the size of the quantum wells. And there's some layers to let current through and to keep light from going out the top. But typically with these lasers, you have to cleave them on the end. And then you have to coat them to make the mirrors. And it's kind of time intensive, and it's kind of handling intensive, and it works great. People have machines for doing this. But what if we didn't have to do that? Remember earlier in the talk I told you to remember the distributed Bragg reflector? Okay. This is a thing called a vertical cavity surface emitting laser. It's about a 10 or 15-year-old technology. What it has is those layers we talked about. And so on the bottom here, there's a mirror, and that mirror is a distributed Bragg mirror, that 1D photonic crystal. And on the top, there's another mirror like that, and in the middle, there are these quantum wells for tuning the energy. And this kind of a laser is really, really cool because you don't have to do any subsequent processing. You build the laser, put the contacts on, and it's done. And better than that, which way does it emit? It emits off the wafer rather than along the wafer. And so in terms of putting it in a device or a package, it's great. And okay, so here's the question. iPhone X with face recognition. Anybody else? Yeah? Okay. Everybody who has one of these has a vertical cavity surface emitting laser. Face recognition. Now how does that work, right? I mean, okay, I just assumed initially it just takes a picture of your face and compares it to the picture that it has. But then why couldn't you put a picture here, a flat picture, and take a picture of yourself and get into the phone? That isn't actually what it's doing. It's actually using this vertical cavity surface emitting laser to hit about 30,000 points on your face and get depth information by the time it takes for the light to go around. So it has a three-dimensional topology of your face. And that actually makes it much harder to fool. And you don't see it, right? And the reason you don't see it is because of what? It's an infrared laser, okay? But, in fact, it's there. This is a picture off the web of somebody doing face recognition on their iPhone, and all of those dots are the individual spots. There's actually a little piezoelectric mirror in there to redirect it around like that the whole time. And all of those little dots are the little dots that it's using to recognize the face. So every last one of you that's used one of those phones has shined a laser into your eyes. Why don't we worry about that? Yeah.
Because it's an infrared laser?
Yeah. Yeah, the cornea of your eye actually stops this infrared radiation, so you don't have to worry about it getting in your eye. And the intensity is very low, so you don't have to worry about it hurting your face. And the energy of the photons is low, so you don't have to worry about it converting your DNA into something that you don't want. Okay, great. Let's see, where are we at? We're almost done. This is pretty cool. I really was trying to get this picture myself. I took it off the web, but I just couldn't find anything that would take an image in that wavelength range. And this taught me something else, because, you know, I thought I'd just go get a webcam. Because a webcam uses a silicon chip, and a silicon chip can see this. But of course, what they do in webcams is they don't want it, they want it to look like a fair rendition of color, so they put a filter in it to block out the infrared radiation so that it doesn't go into the webcam. But I thought, okay, I'll just go over and buy one at the bookstore, and I'll just take it apart, take the filter out, and then I can get a picture like this. That'd be awesome, right? I mean, especially if I could bring it in with a movie and show you guys, you know. And so I went over to the bookstore, and they don't sell webcams anymore. You know why they don't sell webcams anymore? Because everything has one built into it. It makes no sense to buy a webcam anymore. Felt like a dinosaur. Okay, let's move along here. Solid state physics, I'm going to talk a little bit about band theory. I showed you this picture of absorption, but that's like would happen in a molecule. And really, the things I'm talking about are solids, so we have to talk a little bit about band theory. So up at the top, we have isolated atoms, and those red things are the wave functions. And again, they're ground states, so there's just one oscillation there. And if the atoms are isolated, and we look at how many states we have as a function of energy, it's just a vertical line. Now we bring them together. This is a little bit like, think about those waves on pools that I was talking about at the beginning. Imagine you have isolated pools. The waves don't know about one another, but now you connect the pools, and the waves can move from one pool to the other. And now you get more complicated wave patterns. And so when you put these together into a crystal, these guys can overlap, and you actually get an energy band. And the cool thing here is that the number of states in the band is equal to the number of atoms that you have times 2 because of spin. And so you can either have a fully filled band and a gap and an empty band, or you can have a half-filled band. And this is a semiconductor, and this is a metal, and I brought along a little visual aid to help us with that. It seems like if there's electrons here, this ought to conduct, right? It's got electrons. But the problem is the electrons are all squeezed together like in this bottle. So when I turn the bottle, the glass beads don't move, right? It can't conduct because there's no place for anybody to go. But if I take a half-filled bottle and I turn it, I can get the beads to move. This is a metal. This is a semiconductor or an insulator. Okay. This is about 6 weeks of solid-state physics. And you guys just had it in one slide. And if you bring me your sheets tomorrow, I'll sign off on them. Okay, so this molecular picture gets replaced by this sort of band picture. Okay, now let's go backwards. Let's ask ourselves the question. We've got waves, electron matter waves, in crystals bouncing off of atoms, and they give us band gaps, and they give us, can we do it the other way? Can we take light waves and have them hit something and bounce off of the somethings and create band gaps and create transparent bands and use this as a way to control light? And the answer is yes. It's like working backwards, but we have these things we call photonic crystals. We already talked about a 1D photonic crystal. That was a Bragg reflector. This is a 3D photonic crystal. And you can see you've got all these little pieces of glass in here. And when light comes in and hits it, it scatters off all of those. And it moves through this. And at some energies, it can't move through it. It's a perfect reflector. And at other energies, it can move through it. And it's like it's a band transport. And we can use this to tune things. This is sort of artificial matter, if you will. It has a periodic structure. There's an atomic component. This one uses these split rings that's comparable to or smaller than the wavelength of light. And by scattering off of these, we can produce interesting properties. We can produce materials with a negative index of refraction. We can do really cool things with this. Yeah?
What exactly would a negative index of refraction do?
Okay, so I put a pencil into a glass of water, and you look at it, and it looks like it bent down this way, right? If I had a negative index of refraction, it would look like it bent the other way. So what I could do is I could actually compensate for a lens that focuses with another lens that looks like it should focus, but which diverges. I can do a lot of optical correction with a negative index of refraction, but it's a really good question because some of the things people are interested in, I really can't win, can I? Come on. Don't play with me. Okay, so are these useful? And the answer is yes. This is an optical fiber, like a telecommunications fiber, and now they're building fibers to control the index with photonic crystals along the length of the fiber. This is a 2D photonic crystal. Lenses that focus below the diffraction limit. Here's one that, I mean, this is just amazing to me, but car companies and stuff are spending a lot of material on a lot of money on acoustic metamaterials. Because you really want cars to be soundproof, but you don't want them to be heavy. So if you can design something, or like if you live near an airport, and you can put insulation in your house, which insulates the house, and which also does not let sound through, that's a really important thing. And so acoustic metamaterials right now, there's like a paper a week that gets highly cited on acoustic metamaterials. But cloaking is the one that everybody likes. That's the one that everybody wants to talk about, right? And so the idea is, how do you know if there's something present? Well, waves come along, and the object blocks the waves, and you get a shadow. So you know that it's there. Well, what if you could put some kind of a structure around the object, which when the waves came through, caused the waves to reform behind it as if it wasn't there? That object would be cloaked. Yeah. Yeah, go ahead.
I'm guessing everybody's really excited about it because most people play video games and everybody loves the stealth power up.
You guys play video games? What is stealth power up?
It makes you invisible, basically.
Well, everybody knows it.
Annoying.
So there's a lot of work on this. The idea of being able to cloak. It's to be able to cloak heat. It's to be able to cloak light. It's a big deal. Okay, so we're just about at the end. And the question is, are we the first species to discover photonic crystals? And as is often the case, no. This is a peacock, and you guys are familiar with the eye and the feather and how iridescent it is, right? And iridescent is a clue. When things are iridescent, when you look at them at different angles and they appear to be different colors, that probably is not a dye. That's probably a photonic crystal. And in fact, if you take electron micrograph images of the little rayons that come off of the fletch there, they have little holes in them, and they have structures in them, and they're different sizes. And that color is coming about because of this being a photonic crystal and the way it reflects light. And the same is true for quite a few different kinds of butterflies. The color of the butterfly is not because of a dye that's in the butterfly that gets absorbed. It's because the scales of the butterfly have these structures to them. And the structures diffract light like a crystal, create band gaps, create reflection bands, and that's why you see the color of the butterfly, and that's why butterflies are like lasers. And that's it. I'm done, but if you have any questions, I'll answer them. But you don't have to have any questions. Did you learn something?
Yeah.
Did you learn something?
Yes.
Good.
Data was useful. I said I learned that my data was useful.
And it can at least be used in talks.
Exactly.
Okay, guys.
What a turn.
You know, it says recording, so I think we're good.
Tomorrow.